Hey guys, here's the first booklet on logarithmic functions. So I'm going to start off by just reading through the notes here. I know it kind of looks like there's a lot, so we're just going to kind of go piece by piece briefly to introduce why we study logarithms and kind of where they come from. So the last unit we talked about was exponentials, and exponentials looked like this equation here, y is equal to c to the power of x. A couple of important things very quickly. C had to be greater than 0, C could not equal 1. You can go back to the previous exponential video to kind of explain why, but regardless, this is going to be important for us in logarithms as well. Exponentials as an inverse function switches x and y. So now instead of y equals c to the x, it's x equals c to the y. C is in the exact same spot, it stays the same, and whenever you get an inverse function, you're supposed to get y by itself. But something you guys have not really studied up until grade 12 is how to get y by itself when it's in an exponent. Well, if it's in an exponent, we can apply a function called a logarithm. And a logarithm will allow y to come down to the normal level. It's not an exponent, it's just on the main line. And it's going to equal log. C becomes a subscript or the base of our logarithm. And then x, which was our answer here, now becomes what's called the argument. So basically, y is going to be the exponent, and log c of x is asking you what is the exponent that gets us from c to x. Okay, and we'll see a couple of examples of that in a second. These two are interchangeable with each other, the y equals log base c of x with x equals c to the y, which is the reason that y in both of these cases is going to be the exponent to the answer. So log is an exponent, and that's what it's solving for. C is the base, C has to be positive, C cannot equal 1, and the argument, the x value, is also always positive. So a couple of introductions there before we get started. At the bottom of the page, just in here, we have a couple of shifts back and forth going from exponential form to logarithmic form and then vice versa. So the pattern is, if I want to write this in logarithmic form, I am going to go log and then base. Well, the base in this case is 2, so that gives me a 2 on the bottom of the logarithm. Then the original answer, the 8, is going to be the argument in the question. And the log answer is always the exponent. So the exponent will always be the answer to the question. So same thing across the board. We go log base 64 of 4 equals 1/3. And if I read both of these examples that we've written down, the amount or the exponent I need to get from 2 to 8 is an exponent of 3. The exponent I need to go from 64 to 4 is 1/3. And this 1/3, we're going to see a little bit more of later, comes from this original formula of a radical that says if you have a fraction exponent, it's the same thing as a radical in some way, where a, the numerator, goes to the exponent, b, the denominator, goes to the base of the root. So 1/3 is the same thing as a cube root. If you use this little mini formula, cube root of 64 is 4. Okay, across the board, same thing. Log base 3 at 1/9 is -2. 3 to the power of -2 is 1/9. That's where that comes from. And then if I was just writing this out, I don't really care what this gets me. It's not necessarily an evaluation. It's just following the pattern as we follow along. If I'm doing this as exponential form, I'm taking the base to the power, which is 4 to the power of 3, and I make it equal to the argument. So I'm just going backwards from the other question, and vice versa. So I'll leave the rest of that page to you guys. But you can follow the pattern, and that allows us to answer the next couple of pages a little easier. Looking at this page says to evaluate. So evaluate means just give the number to the question. So if I do log base 2 of 16, let's say it equaled some value x that we don't know. It's really asking us what is the exponent that allows us to go from 2 to 16. Well, x in that case, or just the answer to the question, is 4, because 2 to the power of 4 gives us 16. An invisible base in logarithms is 10, and that will be the same every single time the base is not provided. So what is the amount, or what is the exponent that I need to get from 10 to 100? That is 10 squared, so the final answer there is 2. What's the exponent that gets me from 2 to 1, or 6 to 1, sorry? Anything that gets me an answer of 1 has to be an exponent of 0. 2 to 1/4, would be -2, right? So it gives me a negative exponent in that case. And then we get into some square root style questions. So we have log base 2 of root 8. I'm going to give this an equal x as a blank on the right hand side. We're going to go 2 to the x equals root 8. This now goes back into the last video on solving exponential equations, where I want to get these to be the same base. Well, 2 to the x equals 2 cubed with that square root around it, because that's what 2 cubed equals. And 2 to the x equals 2 to the power of 3 over 2. There's that mini formula I told you guys is going to pop up, which is right there. The b root x of a, x to the power of a over b. So x in this question equals 3 over 2. Okay, and then in this case we've got same idea. We've got 3 to the power of x equals, let's change the 9 to 3 squared. Let's change the square root 3 to 1/2. So x equals 2 plus 1/2. And x in that case would equal 5 over 2. Okay, I'll leave the rest of the page to you guys. I want you to be careful with h, I, and j, because there will be some definition type stuff that you got to watch for all of them being no solution. Go back to the last page and you'll see why that's the case. On example 6, we're now looking at solving for x in the equation, but we just follow that same pattern. So we go 5 to the -3 equals x. I basically go into it blindly, knowing that the base is going to go to the power of the answer, because the answer is always the exponent. 5 to the -3 equals x, and x equals 1 over 125. Okay, x squared equals 36. So you square root both sides, you get x equals 6. Usually we would take the plus or minus, but the base of a log must be positive. That's from the definition earlier. So you can't take a plus or minus here, it's just positive 6. 64 to the 2/3 equals x. I'm going to change this into radical form. Cube root 64, and I'm going to do something slightly different, where I'm going to put that in brackets and square it there, instead of squaring inside, which is the exact same thing. But now that tells us that we can take the cube root first, which is a little easier, then square it, and that must mean that x equals 16. Okay, so in those questions, we're always going to do the radical first, then the exponent after. Okay, so I'll skip D and E for you to do on your own. This is the last one where we have a log within a log. Well, using BEDMAS, I solve for this first. So what is the exponent that gets us from 3 to 81? That is a power of 4, which means this is the answer in the bracket. So I rewrite the question as log base 2 of 4 equals x. And then what's the power that gets us from 2 to 4? X equals 2. I'm not going to do the graphing at the end of this booklet. You can watch the next video on log transformations to see how the base graphs work. But I'm just going to quickly introduce it in this video if you're filling out this booklet. Basically, we're going to take all the points that we can physically see on this graph from the base graph of 1/2 x, and we're going to switch x and y. Not only the 3 main points that we can see, but also the asymptote from y equals 0 to x equals 0. But like I said, I'll go into that in a little bit more detail in the next video.